Hi, my name is Kevin,
I'm afraid.
My name is Joan.
And I'm Aditya.
and our project is the power adjusting fan. So here are the project aspects that we're going to cover. For wire requirements and goals, we are required to have a microcontroller, at least two different sensors, at least two actuators, mechanical components, circuit elements, uh, Python programming code, and our goals is to provide the functions that most products lack on the in the market and have real world use applications and make mechanical parts entirely out of 3D printing. So for product information, this is our fan, and the unique features about this fan is that it's power adjusting, it scans for the user, and it monitors temperature. And this is our demo. So for mechanical design, these are the parts that we made for the fan. So for the base, we needed to fit the following electrical components. The shape was initially a circle to match the shapes of the fan neck and the fan shroud. However, it wasn't able to fit all of the components that we needed. So this is where it changes to a square. We also made a hole for the IR sensor, but during testing, the IR sensor did not give us the results we needed. So we switched to a temperature sensor and we made an insert for the temperature sensor. And then for the neck, the initial mounting solution was too sloppy. It cannot hold the neck due to the fan blades and the fan motor, but also the slop of the servo. So what we did was that we made the neck insert into the neck and we added a support collar.
Okay, so for the blades, we designed to use a SolidWorks design study to find an optimal blade of 40 degrees with three blades, which basically balances the high airflow with the low motor torque. And we also reduced the diameter of the blades from 190 millimeters to 180 millimeters in order to ensure clearance within the shroud, eliminating noise and mechanical friction. Also, for the hub features, we use a rivet internal structure, which is basically reducing the weight and the material usage while maintaining a high structural strength. For the fan shroud, we initially started with 1.5 diameter supports that were too unstable for the 3D printer. So we thickened them to 3.5 millimeters for better rigidity. We also expanded the hub to support spacing from 7 millimeters to 9 millimeters. With all these changes, we ensure the blades have enough room to rotate freely without obstruction or vibrating during the operation.
And so with the electrical design, this first slide gives an overview of the components used in our design. The Raspberry Pi Pico RP2040 was the main microcontroller chosen. An important design point is that all three electronic blocks share a common ground, which is necessary for the system to work consistently. For the components, the system uses two main sensor inputs, a Seed Studio Grove ultrasonic distance sensor and an SHT40 temperature and humidity sensor. For actuators, we use two SG90 servo motors for angular motion and a GA12 N20 DC motor for the fan blade. The DC motor is controlled through an L298 motor driver due to spec requirements. In the first block, using the motor driver prevents the Pico GPIO pins from being overloaded and also allows the motor to use a voltage supply separate from the Pico's 3.3 volt logic system. Instead of tying ENA directly to a constant voltage, ENA was connected to a GPIO pin, which allowed us to code it as a pulse width modulation variable for speed control. By changing the duty cycle based on distance feedback, the Pico adjusts the RPM of the fan so when the target is farther away, the system can increase the duty cycle and run the fan faster. In the second block, the two SG90 motors are used for neck motion of the system. Each servo has three connections, signal, power, and ground. The signal pins are connected to GPIO pins on the Pico, while the power pins are supplied separately through the second channel of the power supply due to power demand. Lastly, in the final block, the temperature sensor acts as the first condition for activation. The system keeps reading temperature, and once the value goes above the chosen threshold, the rest of the system is activated. For the voltage supply to both the sensors, the Pico supply was sufficient, and the SCA SDI pins were tied to GP 6 and 7 since they're valid for I2C bus communication. Then the ultrasonic sensor, connected to Grove 1, becomes the main feedback sensor. It detects whether a target is in front of the system, as well as providing a distance feedback, which affects two parts of the behavior, the servo's stop scan mode and feedback to control the fan speed through PWM.
So for the programming, each of the components like the temperature sensor, the ultrasonic sensor, the servo, and then the motor, they're all given each modular functions. And the system is in like a while true continuous loop, and the temperature is read through the I2C. So the temperature is below the given threshold of 25 degrees Celsius. It's idle. If it's above that, it starts scanning. And when it starts scanning, the two servos sweep across the whole range that we gave it. So from 180 0 degrees to 180 degrees. So that's the uh, threshold for the servo. And when it detects someone, it locks at that angle, fan starts spinning. The DC motor is controlled to the PWM based on the distance we gave it, so 0.5 centimeters to 70 centimeters. And for the servo is um it, servo converts the angle into PWM signal, and because the servos receive the same duty cycle, they sync up while they spin.
All right, for the alertness and improvement, basically electrically, we learned that PR sensor require active motion to trigger and that our motors needed separate power channels to handle the load. Mechanically, we focus on optimizing the blade weight to improve motor efficiency. And what we could have done to improve this project, we could have consolidated the wiring into a single power source and add a peer assembly for the next servo to fit the structure's sloppiness, which will in fact also improve the target accuracy when the user is angled at 90 degrees.
So what we covered in this presentation is that we created a fan with power adjusting, tracking, and temperature monitoring features in order to fulfill project requirements. We also demonstrated its functionality in the real world. We also explained the individual aspects of this project in depth, and we discussed the learnings and improvements that we gained from this project. Thank you for listening.